Here we go. Doing 3 ways that heat is transferred. The first way is by conduction. 3 different ways. First way, conduction. This is when 2 objects with different temperatures are touching. When objects with different temperatures are touching by conduction. You remember when we were studying static electricity, charging by conduction, we touched an object. Like we took the plastic rod or the strip and touched the packaging peanut, charging it by conduction. Thermodynamics, heat is transferred by, one way is by conduction when 2 different objects are touching each other. Okay, good with that? And what's happening microscopically, the molecules in the hotter object are moving more, and when you touch something, there's a bumping into the slower moving, colder object, giving it some of that kinetic energy, making it warm up. Okay, charging by conduction. So what I would like you to do is I would like you to go around the room and touch different materials, things that are not living, things that are not electronic, and any ice in the cooler. Any what? Ice in the cooler. If you find it, don't, you're like, oh, okay. Like, don't touch that. Touch different surfaces, different materials. Go around. Oh my God, put on the ice. Don't touch it. No, we said like what feels colder, but obviously the ice. You'll see. What about the styrofoam? You can touch the styrofoam. I'm trying. How many things are we allowed to touch? Are we gonna get a 0? Yeah. Then I'll drop it. Yeah. It's kind of like a.
It was like a weird Mandela effect. Everyone just forgot that there was a worksheet. And I was in English before, and I was like, "Is there a worksheet?" And everybody was like, "Yeah."
Yeah. Yeah, it was, yeah.
We debated it for a solid 10 minutes. We're like, no, it's tomorrow.
Okay, come on back. Okay. What materials felt the coldest? What ones had the lowest temperature? Okay. So if things sit in a room for a very long time at different temperatures, what do they tend to do over a long period of time? Reach an equilibrium. All these objects that you touched have been in here for, well, we'll say a very long time.
You're welcome.
So we can conclude that they all have the same temperature. They're all at room temperature. You okay with that? But why did the metal feel colder? Okay. That is because metal has a higher coefficient of thermal conductivity. Metal has a higher coefficient of thermal conductivity. Another way to say this is metal is a better conductor of heat. Okay, so metal has a higher coefficient of thermal conductivity. It's a better conductor of heat. Okay. Which is hotter, you or the objects, the inanimate objects in this room? You. Hopefully you're 98 point something. And the objects in this room are around 70 degrees. Okay. So which way is heat going as you touch? Out of you into the other objects. Metal just has that process happen faster because it is a good conductor of heat, versus wood is not a very good conductor. And so heat is being transferred from you to the wood, just not as quickly as it was from the metal. Good with that? Okay. So when you check on your pizza or your cookies, whatever it is you're baking, sometimes you get your face in the way and you open the door and it's like you're like engulfed with hot air. Like, whoa, that's hot. That air was 450 degrees. Imagine your face being engulfed with 450 degree metal. You wouldn't get this, whoa, that was hot. You'd be like, like, right. Okay. So air is a poor conductor of heat. Um, it does not transfer its heat as readily. Mm-hmm. Good with that? Okay. So correct answer is D. Lowest thermal conductivity, air. Air is actually a really good insulator. Okay.
We can't spell today, y'all.
All right. Come on back here. Quick little demo. 2 blocks. I want you to feel each. And then
It wasn't me.
And then once you've felt them, move on. Just stay back there. Okay, which one feels colder? Okay, that one is more, sorry, this one is aluminum. This one's plastic. Okay, now, thank you. I'm going to take a piece of ice and put it on each one. What? Wait. Which one felt colder?
The right one.
The one that's melting the ice faster. Like what? Have a conversation about why the one that felt colder is melting the ice faster.
I know, it's very cool. I just tried to have it slow down.
Yeah, but slow. Less.
I can only eat ice cream. I love Chick-fil-A ice.
That one doesn't even melt to the ice cream.
Okay. So, which is hotter, the block or the ice? The block. So which way is heat going? From the block to the ice. Which one is causing heat to transfer to the ice faster? The aluminum, the one that felt colder because heat was being transferred from us to the block faster than it was in the plastic. Therefore, there's heat being transferred to the block of ice. Sorry, not the block. The ice cube faster from the block here than it is here. Aluminum is a good conductor. Plastic is a poor conductor, a good insulator. Good with that? All right, have a seat.
I have both. I have no water. And I actually sprayed that cover for my head air up for this. That's it. Let it get orange state. I didn't mean to. He's just like, oh, what happened by? I was like, in my bag. So I took out and like wrapped it by the zipper for my and I took it out and like pressed down on the top. It was like a straight line just. Oh my god! I would have been dead. But like it looked like spiral, like orange webs. But yeah, we had to air out 2 hours, and now there's no more dark spots. It's okay. I was thinking smoothie and forgot the blade stopped spinning, and I started smoothie and then I took the blade. And I love smoothie all over the smoothie. I'm so serious.
All right.
You know what's that?
Yeah. Well, no, I don't. Correct answer is. Oh.
Wait.
Correct answer is A. Read the order of the heat transfer. Okay, good. Next question.
What?
I said that makes so sense. That makes a lot of sense.
That makes so sense.
It so makes sense.
That is something that your smiley would say. Guys, I'm not getting it. It makes, wait, what was it? It's so sense? It makes sense. I'm gonna see that on your slide one day.
Okay.
He's like, shut up.
Correct answer is
Okay.
educated elephants. And so air is a bad conductor, therefore it is a good insulator. Okay. We use the same descriptors, like adjectives, as electricity. Conductor, insulator, heat, conductor, insulator. Okay. They don't always mean the same thing. Sorry. The materials aren't always the same in terms of what's good conductors and insulators, but we use the same way to describe that. Heat is being transferred. Okay. So air is a good insulator. It is a poor conductor. Okay. Loaded question. Is there such thing as a perfect conductor or insulator? No. You get close, but nothing's perfect. Okay. Specific heat capacity and thermal conductivity are often confused. They're not the same thing. But there is a trend. But it's not an always thing. It's a usually thing. Okay. So metal has a low specific heat capacity, meaning it changes at temperature with a small amount of energy. It usually allows heat to transfer through it quickly. For example, if you've ever used a metal spoon to like stir your coffee or oatmeal or hot chocolate, like whatever, and after a while that the handle of the spoon becomes hot or warm, how quickly the heat travels through the metal is a consequence of thermal conductivity. How much the temperature changes by, that's a consequence of thermal conductivity. Nope. That is a consequence of specific heat capacity. Let me say that again because I just messed that up. How much the temperature changes is a consequence of specific heat capacity. How quickly the heat transfers through the material is a consequence of thermal conductivity. Often, high thermal conductivity has a low specific heat capacity. An example of where it doesn't work is lead. Lead has a low specific heat capacity. To make a connection with movies, is Patriot, like Mel Gibson, is that a thing in your childhood? He melted the little toy soldiers and the musket balls of the fire. Like, it doesn't take much to change the temperature of lead, but lead is a poorer conductor. It does not transfer heat readily. So theoretically, you can dip your hand in molten lead fast and it doesn't get burnt. Mythbusters did a thing on that. You like, don't try it at home. They like did a whole bunch of experiments where on a hot dog where it burnt the hot dog till it got it just right. But that's the one example. But usually they correspond. Cool with that? It's a usually thing. For a given amount of energy. How quickly heat transfers through a material. You do that? All right. The second way heat is transferred. Conduction is the first. Convection is the second. This is where this happens with fluids. Fluids can be a liquid or a gas in science. Have you ever heard the expression heat rises? That's convection. Okay. This is due to when a fluid is hot, it is less dense than a cold fluid of the same type. And because it's less dense, it floats on the more dense cold fluid. Okay. Just like wood would float in water because it's less dense than water, hot air floats on cold air because it's less dense than cold air. You can see this demonstrated if you ever stood in a building that has a loft and you go up to the loft, it is hotter up there than it is down on the main floor. Good with that? Hot air balloons, the hot air floats on the cold air. That's why it lifts up. Okay. You can also see this demonstrated with if you're boiling water in a pot, you can see some impurities in the pot where the little bubbles are starting to form, and they'll rise up and then they'll cool down. So you can see the convection currents. Okay. Convection oven has a fan in there to kind of mix things up, mix up the hot and cold air. Good with that? Tell your neighbor. Everybody playing along, okay with C? Okay. Now, in your house, in rooms, if you have central air, you'll have two vents in your room. One's usually near the ceiling, one's usually near the floor. One pumps air into it, the other draws air out of it. It's called the return. Okay. And whether it's like the top one blows it in or pulls it back, it depends on the design. There's no really standard, but one's blowing air in, the other one's sucking air out. Good with that? All right, this is cool. On a beach, you can check this out this summer if you go to one. Even Lake Michigan works. This works. So the sand, because it has a low specific heat capacity, gets hot. Heats the air right above that, and then because of convection, that hot air rises, leaving this vacuum or low pressure. So cooler air from the sea or the body of water comes in and replaces that. So during the day, you always get this sea breeze because of this convection current. Okay with that? That's why people fly kites or, do like, there's always that wind at the beach. Okay. But check this out. At night, which one's hotter, the water or the sand? The water is warmer. This process is reversed, like after midnight or something. After what, like when the sand feels cold, Next time you're at the beach, go out like late at night and like, or like right before dawn, like get up before the sunrise or at sunrise and take note the temperature of the sand and the direction of the sea breeze. It should be going out because it reverses that process. Cool that? Okay. Well, I hope it's not conduction. That would be bad. Convection, there's no fluid between here and the sun. So it must be the third way, which is radiation. Okay. These are electromagnetic waves. Remember when we were talking about electromagnetic spectrum? Okay. And this is the infrared rays or infrared waves. Okay. So we can pick these up on infrared cameras as thermal imaging cameras. So here, like, this shows the efficiency of a workout machine. Like, look at those abs. They're just burning, like, they're just burning fat and all that stuff. Okay. Thermal imaging, this is how Predator sees. So this is picking up thermal signatures, soldiers. This is not night vision. Night vision takes the small amount of light that's being reflected and amplifies it. But you can use this to see at night or see behind walls or stuff like that. Okay. You can take thermal imaging cameras and do like an inventory of like how well your house retains heat. So notice where the heat is escaping out into the atmosphere. The top and also windows. So if you ever go shopping at like Menards or Home Depot and you like are checking out insulation, insulation is rated on different, like it's an R value. The higher the R value, the better the insulation. Windows have such abysmal R value that they actually came up with a whole nother scale so not to depress the consumer. Like Windows have an R value of like 0.002 or something stupid, ridiculous like that. So you lose a lot of heat out of Windows, even if you have good Windows. But if you have bad Windows, they're like really bad. Some you can like feel the draft coming in. Here's that. And then you got some temperature currents. All right. If you are okay, I'm just going to tell you this factoid here. If you are above absolute zero, which is everything, you are emitting electromagnetic waves. You're emitting infrared waves. Okay. You are also absorbing infrared waves. If you are hotter than your environment, hotter than your surroundings, then you are emitting more than you're absorbing. Does that make sense? If you're hotter than your environment, you're emitting more than you're absorbing. But if you're colder than your environment, you're going to be absorbing more than you're emitting, because you're trying to attain thermal equilibrium. Does that make sense? Okay. So if you're colder than your environment, you're going to be absorbing more infrared rays than you're emitting. Good with that? Okay. So nope. There it is. All right. Good emitters. Examples of objects that are good emitter of radiant energy. Dull black, like a flat black rather than glossy, is a good emitter of radiant energy. Shiny white, like glossy or silver, is a poor emitter of radiant energy. Oh, forgot a ruler. Do you want a ruler? Okay, sorry. Welcome. Okay. Things that are a good absorber of radiant energy. Dull black objects are good absorbers. That's exactly why. And poor absorbers are shiny white. Okay. Here's one summary. Good absorbers is good emitter. Okay. Poor absorbers equals good reflector. Okay. If you're a poor absorber, that means you're reflecting. What's reflective? Well, shiny white silver stuff. It's reflective. It reflects light, like visible light, but it also reflects infrared waves. Does that make sense? Versus dull black, it's a good absorber. But if it's a good absorber, that means it's also a good emitter. Good with that? Okay. This is the easy, based on experience. Okay, you want to walk on the white parking lot lines. Why? Because blacktop is a good absorber of radiant energy. where the white lines are good reflectors, they're poor absorbers. Good with that? But check this out. Let's say after midnight, you're walking across this parking lot barefoot. You know, why not? And which surface is going to feel warmer? Turns out the white, because the black is a good absorber, but it's also a good emitter. It's going to cool down faster. It's going to emit radiant energy off fast. Do what? We can test that. We'll get.
Smiley emails us, all right, guys, show up at 12 a.m.
Okay, here's some other examples of radiant energy. So we wrap aluminum foil around food. Aluminum is shiny and reflective. It's reflecting the radiant energy back into the food. Okay. Have you ever seen space blankets or like those survival blankets that are like, they're like shiny? I kind of liken it to shiny trash bags. Okay. Sometimes they'll put that around runners after the end of a marathon. It's not something you'd think, oh, I'm going to snuggle up with my little plastic trash bag, shiny trash bag, but it reflects the radiant energy back to you, keeping your muscles warm. Okay. Thermoses, there's a shiny surface on the inside. Radiators, so your car radiator, these are like the metal plates in the front of your car. They're made to be a good emitters of radiant energy. They want to get rid of heat as fast as possible. So they're made of dull black metal to radiate heat away quickly. Some space heaters, we'll get there. I'll go get that. No, we won't be here when it's cold. Yeah. So, got a worksheet due tomorrow. So this is a space heater. Acts like a flashlight. Looks like a fan, but doesn't work like a fan. So this is red hot. So what you would feel is nothing, 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 nothing. Wow, that's hot. Nothing, 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 nothing. Wow, that's hot. Nothing, 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 nothing. So as this acts like a flashlight, as the beam shines on you, you're feeling the heat. It's like if someone you're at a bonfire, and someone stepped in front of the fire, casting a shadow on you, you feel the heat drop immediately because they're blocking the radiant energy from the fire.